Hi, thanks for watching this presentation. My name is Babak and it's my pleasure to present to you our recent work which is published in Nostaf 2021 workshop. The title of our paper is Understanding Quality of Experience of Heuristic-based HTTP Adaptive Bitrate Algorithms. This paper is available at ACM Digital Library and free to be downloaded. I hope you enjoy watching this video and find it useful. I will start with an overview of the paper in three sections: the main idea, the platforms which we have used, and the participants, plus briefly introducing the test sequences used in our experiments. The main idea of the paper, as the title indicates, is to evaluate a set of well-known ABR algorithms in HTTP adaptive streaming. We have conducted subjective and objective evaluations to find out how good can these ABR algorithms perform in different network scenarios. We have used CADWise as our testbed, which is an open source cloud-based platform for testing ABR algorithms or media players. This software is available in GitHub repository and you can use it for your own media player assessments. We used Amazon Mechanical Turk, or in short form mTurk, to conduct our subjective evaluation. I will briefly introduce this platform and our portal in next slides. In total, we had 835 participants in our subjective evaluations, out of which 780 participants had at least one vote with the correct answer to the content-related reliability question and managed to cast their votes before the submission timeout. There are 4 test sequences that we have used for our experiments: Sintel, Volcama, the famous Big Bug Bunny, and Tears of Steel. All of these test sequences are available to be downloaded for free on the internet. In total, we have evaluated 7 ABR algorithms, which is listed in this slide. Dash.js version 3 with the ABR algorithm named Dynamic. This is a combination of throughput-based and BOLA algorithms. Shaka Player version 3 with a throughput algorithm that uses throughput heuristics with an exponential weighted moving average smoothing function. BBA0, a buffer-based ABR algorithm that uses the current buffer occupancy to select the bitrate for the next media segment. Elastic, which is a hybrid ABR that uses feedback control theory, which generated the long-lived transport control protocol. And the next ABR algorithm is FastMPC. This is also a hybrid algorithm that uses a model predictive control approach. And the last one, Quetra, which is a buffer-based algorithm that formulates ABR decisions as a queuing theory model. Other than the default ABR algorithms for Dash.js and Shaka players, we have implemented the mentioned algorithms using JavaScript on Dash.js media player. Objective evaluations and network simulations. There are 4 different network profiles that we have used in our experiments in this paper. Ramp down profile, which is shown on the left side of the figure 1 with a blue line, mimics a network profile in which the available bandwidth starts from highest possible bitrate and gradually reaches to the minimum available bandwidth. The highest amount is around 7,000 kilobit per second, and the steps of reducing bandwidth here is 10 seconds. Also, the minimum available bandwidth in this network profile is around 250 kilobit per second. In ramp-up network profile, we increase the available bandwidth for each client from the minimum to the maximum possible bandwidth. Mean and max and the incremental steps are similar to ramp-down profile. To provide a more challenging network profile to the clients, we have designed fluctuation network profile as well. In this network profile, we constantly decrease to the minimum available bandwidth and increase to the maximum available bandwidth with the interval of 10 seconds. This network profile is the most challenging, and in contrast, we have also introduced a stable network profile in which the available bandwidth is constant and set to the average available bandwidth with no fluctuation. You can see these two network profiles, fluctuation and stable network profiles, on the right hand side of the figure 1. The streaming session will be recorded in database in form of streaming session logs, and these logs will be used later for calculation of the objective MOS using P1203 quality model, and also will be used to stitch the media segments together and generate a single MP4 file. The MP4 file will later be used for subjective evaluations, and participants will watch these MP4 files and cast their votes with a range of 1 to 5. As mentioned in previous slide, we record the streaming session logs in database. Among the data that is being stored, here are the significant metrics for our evaluations. A startup delay, a stall events, and also the requested segment bitrate. The average stall event duration is shown in figure 2 on the left side, and it's recorded in seconds. On the other side, you can see the average startup delay for each media player or ABR algorithm. Obviously, the less the numbers here are the best in both a startup delay and stall events. For example, for elastic ABR algorithm, you can see the average stall event duration in ramp-up network profile is indicated as 0, which means this ABR algorithm could continue the playback in all experiments with different test sequences without any stall event or rebuffering. Also, fast MPC ABR algorithm has the highest average stall event duration of 73 seconds in fluctuation network profile, which will be very much annoying for the end user. All of the ABR algorithms have almost same startup delay except for Shaka player in ramp-up profile, which is around 10 seconds. After calculation of the objective MOS or mean opinion scores, using the ITUT P1203 quality model, we have also conducted the subjective evaluations. The results and findings are presented in this slide and also in the next slide. Here you can see both subjective and objective evaluation results. Blue columns are representing the objective MOS and the orange columns are representing the subjective MOS. In both cases, the range of scores are between 1 to 5, in which 1 stands for worst experience and 5 stands for excellent quality of experience. As it can be seen, Shaka player default ABR algorithm and BOLA algorithm with the subjective MOS of 3.73 had the best performance in ramp-up network profile, and the BOLA algorithm had the best performance in ramp-down network profile with the MOS of 3.65. In this slide, you can see the results of the evaluations for other two network profiles, namely fluctuation and stable network profiles. 3.39 was the highest gained subjective MOS, which shows good performance of BBA0 algorithm in a tough network profile such as fluctuation. And Dash.js default ABR algorithm has the best performance in a stable network profile with a MOS of 3.98. Other than the discussed evaluation scores, we have also calculated the Pearson's correlation between the two types of evaluation that is shown on the top right corner of each chart. To conclude my presentation, I want to summarize the contributions of this paper and also mention the possible future work that we have in mind. We have evaluated 7 well-known ABR algorithms in this paper. However, these ABR algorithms are just heuristic-based ABR algorithms, and in future work we want to also include learning-based ABR algorithms. This paper's main contribution was to investigate the correspondence of subjective and objective evaluation for a set of well-known heuristic-based ABRs. In the future work, we also want to include other quality models other than P1203, which we have used in this work. We have introduced 4 network profiles which were simulated using our testbed but in future work we also want to use real network profiles or traces. And also another direction that we want to go through in the future work is to have deeper statistical analysis over the findings and obtained results. Finally, I would like to thanks to my co-authors and also the Nostalgia 21 conference reviewers. My co-authors are Dr. Bentale, Professor Timmerer, Professor Zimmerman, and Professor Hellwagner. Thank you for your attention. My name is Babak, and I wish you a very good time ahead.